Sir, it is better. We think that it is most important how to analyze the the data, how to analyze the data.
Okay, sir. Now it's visible, sir.
Okay, ma'am. Okay, ma'am.
Okay. Thank you, sir.
Sir, hello, sir. Hello.
Ma'am, is it visible to you, ma'am? Agenda?
Yes, sir. It's visible, sir. Agenda is
Okay.
visible. Okay, sir.
Right, ma'am. Okay. Okay, actually, this is the device which is optical microscope. Actually, I have just entered into the principle behind the optical microscope. So this is the diagram I would like to show. Actually, there are basically two different nature of specimens. One of the specimen is the transparent nature of the specimen. So for that, the diagram which is available on the left end will provide the basic principle of working of that machine, optical microscope. So here I already told that actually the working medium for this optical microscope is the light rays. So that light rays are obtained from a light source here, that is the lamp. So that lamp is providing the light ray over the condenser lens. That condenser lens will focus the light ray on the specimen. So the specimen is having the darkness as well as the transparent nature according to its structure. So when the light ray passes through the specimen, actually that light ray will carry the inner structures of the specimen. So thereafter it will fall on the objective lens. Now that objective lens will magnify the images which are obtained through the light ray here. Actually, the objective lens can magnify up to 100 times of the size of the image which is available on the specimen. Actually, up to 100 times. What I want to tell is actually based upon the gap or distance between the specimen and the objective lens, that will decide how much times that object is to be magnified. So it can magnify up to 100 times here. Thereafter, that magnified image is allowed to fall on eyepiece lens, where it is further magnified for 10 times. So if it is, if the image is magnified in objective lens for 100 times and it is magnified in eyepiece lens for 10 times, totally 100 into 10, 1000 times that object can be magnified in an optical microscope here. And if the specimen is of the nature of, actually if the specimen is having the nature of opaque nature, we have to look on the right side diagram. Actually in that diagram, the sample is available at the bottom, and that is a opaque specimen, so it is not having any transparent nature, so only it can reflect the image. So the light rays are available on the light sources available on the right side, from where we are receiving the light ray that will fall on condenser lens. It will focus the light ray that will fall on the slanting mirror, actually semi-reflecting mirror. That is one of the mirrors available at the bottom that will reflect the mirror towards the downward direction. That light ray will come towards downward direction and fall on the sample where it is reflected. Actually that reflected image, that is reflected light ray will have the nature of the specimen which is available. So that reflected image will be passing through the objective lens where it is magnified. Thereafter it will allow it to pass towards the semi-reflecting mirror which is available at the top here, where it is reflected and it is diverted towards the actually eye observation. Actually that is the ocular lens, that is nothing but eyepiece lens here. So on that eyepiece lens, it is eyepiece lens, it is falling, where it is further magnified up to 10 times, and by using our open eye we can view the magnified image of the specimen. By using a photographic sensor also we can make the photograph of our magnified image. So for that category we are using
voice not there.
Excuse me, sir. Kindly unmute, sir. Srinivas, sir, your mic is muted. Please unmute. Srinivas, sir, your voice is not audible. Please unmute.
Sir, can you hear me, sir? Sunil, sir?
Yes. Please proceed.
Okay, sir. Okay, sir. Now view is it visible? Optical microscope diagram, schematic arrangement.
Yes, sir. Yes, sir.
Okay. Okay, ma'am. Actually, this is the schematic arrangement of the optical microscope. It consists of three basic components: base, arm, and head. Base part is having the that is the bottom part of the machine, and it consists of a light source. Actually, there are two light sources which are available on this machine. One of them is available at the bottom. That is the lower illuminating element. Actually, that is available at the bottom, and over that is used to supply or transmit the light ray towards the upward direction, and that stage plate is used to carry the transparent specimen here. Actually, that is used to carry the specimen, and that stage clips are used to hold the specimen, and the arm is containing a focus control. Actually, that arm is supporting the head part of the machine. That arm is also having a controlling knob. That controlling knob is used for moving the head towards upward and downward direction for focusing the light ray on the specimen here. So thereafter, in the head part, we are having objective lens, where the images which are obtained from the light ray will be magnified, and further it will be taken to the eye cups. And trinocular part is also there, that is used for taking the photograph of the magnified image. So when we know the working principle, we have to keep our specimen on the stage plate, and we have to provide the illumination, that is the light source. When we are providing the light rays over the specimen, it will that light ray will carry the inner structure of the specimen when it passes through. So thereafter, that specimen actually that light ray will be taken to the objective lens, where it will be magnified. Thereafter, it is taken to the eye cups, where it will be further magnified for 10 times. Then on our eye cups we can view the magnified image of the specimen here. So maximum magnification we can obtain here is the 1000x. The main drawback of this element, actually this component is this machine is only it can magnify up to 1000 times, because the resolution of our visible light ray is very minimum. So we cannot magnify beyond this limit here. And these light rays are also having diffraction ability. So due to that, we are having only the resolution up to 0.2 micrometer. So those are all the drawbacks as well as statistics related to this optical microscope here. So the types of specimen which can be viewed on the optical microscope is the biological specimens. So by using this optical microscope, we can make a transverse section as well as lateral view, and we can also actually this not only the botany specimen, actually the zoological specimen can also be viewed by using the optical microscope here. So nowadays, actually right from the olden days itself, this optical microscope is used for the medicinal purpose. Actually, medical diagnosis purpose, we are using the optical microscope here. And other specimens are powders, fibers, flakes, metals, alloys, composites, ceramics, and powder metallurgy products here. So this is the area. Actually, my area is the natural fiber composites. In one of my paper, I have analyzed the ingredient of that natural fiber composite. The main ingredient is the natural fiber. So that natural fiber is obtained from a plant. I have utilized the Sansevieria cylindrica plant as a fiber source. From the leaf of the plant, I have extracted the fiber, and after extracting the fiber, I have identified some sort of size differences there in the fiber. So due to that, I have gone for microstructural analysis. So in my microstructural analysis, I have utilized the optical microscope for viewing the leaf of the cross-sectional view of the leaf of the Sansevieria cylindrica plant is viewed in optical microscope here. The diagram which is indicated as 6A, that is at the center, that will provide the transverse section of the Sansevieria cylindrica leaf here. Actually, on the right side of the middle diagram, a light blue color line is there. That will indicate the outer periphery of the Sansevieria cylindrica leaf here. Actually, what I have learned or what I have observed from this diagram here is, I have observed what is the cross-sectional shape of the fiber. What is the nature of the fiber? Actually, what is the cross-sectional shape of the fiber? Whether the fibers are having or any variation is there, and where actually what is the nature of distribution of the fiber, whether the fibers are available nearer to the outer periphery or it is available at the center of the leaf, or those things I have learned. Actually, from the observation, I have identified from the middle diagram, if you see there, at the center, actually nearer to the outer periphery, we are having a polygonal shape of fiber. That fiber is called the structural fiber, that is magnified on the right side. And one another fiber which is available nearer to the center, so that fiber is called as arch fiber. So that arch fiber is magnified on the left side of the left side diagram. Actually, so from this observation, I have identified there are two different categories of fibers which are produced by the Sansevieria cylindrica leaf. One of the fibers is structural fiber and another one is the arch fiber. So those things I have learned, and not only this one, related to this, when I magnify that fibers further, I have identified the inner elements of the fiber. Actually, that fiber is having fiber cells. Within the fiber cell, it consists of fiber wall, that is the primary wall, secondary wall, fiber lumen, as well as middle lamellae. So those elements I have identified. And the most important thing is fiber lumen. That fiber lumen provides, actually, that fiber lumen is the vacuum part. Actually, that is the fiber lumen is the orifice or the porosity available on the fiber. Actually, from that I have identified this fiber is having around 67% of porosity on its structure. actually that porosity plays a vital role, because that reduces the weight of the fiber. Actually, that porosity reduces the weight of the fiber, and it can also be applied for any sound insulation purpose also. Sound insulation panels can also be created by using this fiber here. So for that purpose, that fiber lumen analysis is used. So thereafter, I have also identified the analyzed the lateral surface of the Sansevieria cylindrica fiber. So that lateral surface analysis is needed mainly for identifying the interaction between the fiber and matrix when it is utilized for composite generation. Actually, during the composite generation, that fibers are incorporated or kept on a resin. So at that time, the interfacial bonding between the fiber and matrix plays a vital role, or plays a deciding role on the strength of the fiber. So in the for that purpose, I have analyzed the lateral surface of the fiber. This lateral surface of the fiber consists of lot of pits, and that is, it consists of a lot of ups and downs. So totally the surface is rough. So actually that rough surface facilitate the interfacial bonding between the fiber and matrix when it is utilized for composite generation. And I have also, after analyzing the elements on the optical microscope, I have also utilized the magnified images for measurement. Actually, by using ImageJ software, I have identified the cross-sectional area of the fiber, because it is having polygonal shape and irregular polygonal shape. So due to that, the cross-sectional area of the fiber is analyzed with the assistance of the ImageJ software. Not only the cross-sectional area, I have also identified the porosity fraction, how much amount of porosity is available on the total area. So that also identified, and the thickness of primary wall, secondary wall, fiber lumen. So those things also identified, because that plays, actually the thickness of the primary wall decides how much quantity of cellulose which is available on the fiber. So each and every element is related to some of the chemical constituents present in the particular fiber here. So for that purpose, I have analyzed the various measurement also on the optical microscopy images here. So coming back to the mechanical part, actually this is the image which shows the tetrafluoroethylene, that is reinforced in a acetal matrix composite. Actually here the magnification level is 165x. So here the worm shaped, actually by using this diagram we can understand, actually the worm shaped elements are the polytetrafluoroethylene. So PTFE, that is the worm shaped elements. So by using this diagram we can understand, or we can identify whether the interfacial bonding between the reinforcement and matrix are proper or improper. Whether the PTFE is having uniform distribution nature or not, whether that PTFE is floating on the specimen. Actually, if the density of the PTFE is very, very lesser than the acetal matrix, then the floating of PTFE will occur. If the density of the PTFE the reinforcement is greater, then it will come to the bottom and stay at the bottom. So at that time, the distribution of the reinforcement within the matrix will not be proper. So that actually, whether it is uniformly distributed or not, that can also be identified. The size of the PTFE particles can also be identified. So those things can be identified with the assistance of this diagram here. So similar to this, on the cemented carbide microstructure, I have we can identify the different elements which are present on the particular component. That is the here the light color, actually lighter areas are representing the carbide particles, and the darker areas are representing the cobalt binder here. Similar to that, the influence of carbon content on the annealed carbon steel can be identified with the assistance of these diagram. Here the diagram A, which represents the 0.2 percentage of carbon, and B is having B is representing the specimen having 0.6 percentage of the carbon. Actually, when the carbon content is lower, at the time the ferrite is the dominating element. Actually, the lighter areas are representing ferrite and the darker areas are representing perlite. When the carbon content is lower, the ferrite is the dominating element. So the properties of the ferrite is available on the carbon steel when we are having 0.2 percentage of carbon. When the carbon content is increased to 0.6 percentage, it's here the dominating element here is the perlite. So that we can observe from this diagram here. Similarly, the surface finish of the specimen can also be identified with the assistance of the optical microscopy. So here a steel plate which is processed by two different methods. One of them is by hot rolling and another one is by cold rolling. So hot rolled structure is having a rough surface finish, and the cold rolled steel is having the almost, when we compared to the hot rolled steel, it is having the fine finishing. And we can also identify the porosity on the metallurgical part here. So this is the diagram which indicates the surface of the powder metallurgical steel part. Here the darker element is representing the porous things, porous part which is available on the particular specimen, and lighter element is representing the ferrite with perlite here. So finally, advantages of this optical microscope: this is a compact system and it is having very lightweight. Even living organisms can be observed on this optical microscope, and it does not require any backup for its operation, and minimum maintenance only required for this optical microscope here. And disadvantages, I already told. The resolution level of this optical microscope is only up to 0.2 micrometer. So only poor surface view can be obtained when we compare with SEM, scanning electron microscope, as well as transmission electron microscope here. And the lower magnification, only up to 1000x we can obtain here. And it cannot provide the three-dimensional observations here. So those are all the disadvantages. And application, this optical microscope is utilized in the mineralogy, medical diagnosis, microbiology, biotechnology, microelectronics, and pharmaceutical research also. So thank you for your patient listening. Thank you.
Thank you, sir. Thank you for your detailed presentation on basics of optical microscopy with relevant pictures. And we hope our participants have benefited from your insights. You have shared your findings and works on a plant Sansevieria cylindrica leaf with optical microscope. Thank you, sir. Thanks a lot.
Thank you.
Dear participants, now we are moving to the second presentations of today's workshop. For that, I would like to call Dr. Satish, an outstanding scientist at Defense Meteorological Research Laboratory, DRDO, Hyderabad. He is working there since 2005. He received his doctorate from Indian Institute of Technology, Hyderabad, in the area of meteorological engineering in 2018. He is from Kodachal, Kanyakumari district, and his research areas includes thermomechanical processing of titanium alloys and superalloys, hot deformation process modeling, severe plastic deformation processes, sheet metal forming, etc. He has authored over 42 publications in international reputed journals, and he is a recipient of a DMRL Laboratory Scientist of the Year Award in 2018. He is a recipient of a DMRL Technology Group Award for the year 2021. Now I humbly request him to share his thoughts, works, ideas on Field Emission Scanning Electron Microscope. Please, sir.
Thank you, ma'am.
Thank you, sir.
Hope I am audible to you people.
Yeah, it's audible, sir. Your voice is audible.
So my screen is audible, by the way.
Yeah, it's visible, sir.
Okay, fine. So thank you for the kind introduction. Before I start anything to it, I would like to thank Professor Lalu for this warm invitation, and also like to thank the entire team behind this online workshop. So I'll be talking something about the field emission scanning electron microscopy. I'll be covering the main aspects or the key aspects of this particular microscopy thing. So my outline of the talk would be like this. I'll be giving an introduction. Then I'm happy that we had a optical microscopy session just before us. So I'll be giving a comparison between the light optical microscopy and SEM. We'll talk something about the history of the SEM, its working principle, and the different components involved in an SEM system. And I'll be covering maybe two very important imaging techniques that are very commonly used during SEM imaging. And I'll be finally coming to the applications of the SEM-based techniques. So for more reading, I hope the most of the things what I have I'm going to present in this coming slides are taken from these two particular textbooks. And for better reading, you can probably follow these textbooks if at all somebody is interested. So before I start, I would like to give a glimpse about how FESM is important in day-to-day life or in the current scenario where we are being stuck with the pandemic and it is sort of taking a ride on us. So this is a recent work by Caldas et al. Reported in a recent publication of 2020, and where they were trying to find out the SARS, that is a COVID-19 virus interaction with the hostel, with different time intervals. We can see after 2 hours or maybe after 48 hours how it will have an effect. This is after a 2-hour period, how you can have an effect on it, and after 48 hours how the SARS-CoV is going to change its effect is how the people have tried to look into it. So with this, I will start with this. So just now we had a lecture on the light optical microscopy. So basically the resolution is defined as the minimum spacing between the two features, which can be recognized as a separate and a distinct thing. So this is a classical equation provided by Abbe to talk about the which defines the imaging resolution. D is the resolution what we are talking about, the minimum spacing, and it is a function of lambda, that is the wavelength of the source or the light we are going to use it, and these are the refractor index, and this is the angle what we are seeing. As we can clearly see, the resolution is directly proportional to the wavelength of the source or the light source we are going to use it. So if you look at the entire spectrum of the waves or the wavelength spectrum of the entire scenario, we have light somewhere here ranging from some 780 to 400 to 780 nanometer, whereas we have the electrons which are having the wavelengths much lesser than the wavelengths what we are talking about visible light. So since we are having a much lesser wavelength for the electron beam when compared to the visible light, this is going to give you a better resolution and much higher resolution than a light optical microscopy. So to have a comparison between the light microscope and the scanning electron microscope, as we can see, the radiation which is used, the source of light, the source beam is going to the visible light, whereas in case of a scanning electron microscopy, we are going to use an electron as a beam. The wavelength, as I was just mentioning about, it is having a 380 to 760 nanometer in the range, whereas we are having a much lesser nanometer, at least 2 orders less than what we are having in light. But again, it depends on the accelerating voltage. And we are having glass-based lenses, which has a limited refractive index. That is also going to give a problem with the useful magnification and the maximum resolution. So whereas in case of scanning electron microscopy, we'll be having an electromagnetic lens. And if you recall the earlier lecture where he was trying to give you a glimpse about the 1000 magnification is the maximum magnification what we can achieve with a light microscopy, whereas we can go up to sort of 2 log magnification of useful magnification, and it is possible to even go up to 10 lakh magnification. So if you look at the resolution, as I was telling, the resolution is in the range of 200 nanometer in case of light microscopy, whereas it is at least 2 order down. That is, we can even distinctly see an object of around 1 nanometer in size in the scanning electron microscopy. So if you look at the analogy between the light microscopy and the scanning electron microscopy, or for that matter, even the transmission electron microscopy, which also works on the principle of electron, you have an illuminated bulb as a source for a light microscopy, whereas you have an electron source here in both the cases. And you will be having a objective lens, and the specimen will be kept somewhere here. And the objective lens is going to do the job of magnifying it, and you can see it in a projector lens, and you can see it in an eyepiece. Whereas in the case of scanning electron microscopy, you have a electromagnetic lens. There will be a series of electromagnetic lens which does the magnification job, and you'll have multiple detectors to take care of the imaging part, and the specimen is kept somewhere here. So this is a typical example of how a tin ball looks at different magnifications, starting from here, and the micron marker, this is 1 micron, and we are going up to 100 nanometer. And you can clearly see the resolution is pretty good, and we can able to identify the individual particles, individual balls of tins, and you can even do an analysis to find out the sizes of this tin balls also. So before going into the actual topic, that the SEM and this techniques, I would like to give one slide which gives a history of the SEM development. It was Professor Ernst Ruska, a German physicist at Munich University, was the one who has formulated the framework for understanding the electron trajectory under the electromagnetic field. So this particular framework was basically exploited or used for the invention of this electron microscopy. And for his tremendous work, he was awarded the Nobel Prize in the 1986. So if you look at, these are the key developments that happened in the field of SEM. As we can see, the concept of SEM was proposed by Knoll. It was none but the PhD supervisor of Professor Ernst Ruska in the year 1935. And the first SEM was developed in the year 1937-38 by, again, another German physicist, von Annai. And after that, there were a couple of developments happening in US and UK, where people are trying to, the first scanning electron microscopy which was developed was having a resolution of 100 nanometer, which was improved till further by around 50 nanometer. So the another breakthrough happened in the year 1960, where Ewart and Thornley came up with an electron detector, which is an important component of a scanning electron microscopy, wherein you can trap the electron and you can image the observations from a sample. So again, moving to the 70s, this was a place there was a major breakthrough again, wherein people started coming with the field emission guns, as well as the lanthanum hexafluoride cathode guns, as well as the electron backscatter diffraction, which is a very useful and the beautiful technique for capturing the crystal structure and grain orientation. So further to that, there are a lot of developments in case where we can do an imaging by the automotive mode, and we have also having a variable pressure SEM for samples which get charged because of the electron exposure, and we can also come up with a lot of high resolution microscopes to even carry out studies at nanomaterials. So this was a photograph of the very first SEM built by Manfred van Ardon at Germany in 1937. It seems to be a very big one. So the conventional microscope of nowadays, where you can see in the research institutes, looks like this. This is how the scanning electron microscope looks like this, and these are the different components which are present in the scanning electron microscope. You have an electron source located somewhere here. So this is going to be the source for the electrons, and the electrons are going to be focused. This is a sample stage where the sample is going to be placed, and this is the different electromagnetic lenses which will be along the column, along this column, and this is where the place where the sample will be going to be inserted into the scanning electron microscope. And we'll be having a scanning coil here, so which will be doing the scanning from one pixel to another pixel, and that will be transferred as an image to a computer configured to that. And there will be multiple detectors, in fact. So you can have a EDS detector to understand the chemical composition somewhere here, and we can have a secondary electron detector, and we can have some infrared camera to see how the scanning is happening here. And we can have even a backscattered electron detector to capture the backscattered electron. So we can have multiple detectors in the vicinity of the sample, so that we can capture the different types of electrons, and you can do a detailed analysis of each type of electrons that is being emitted by the sample. So the first important part of electron microscopy is nothing but the electron gun. So, so the electron gun, the primary function of the electron gun is mainly to generate electrons by an which will be accelerated downwards towards the column what I have been showing, what I have shown just now. So this the electron generated beam should have the following capabilities or the requirements. The electron beam should be stable with high brightness, and you can see the brightness. This is a function of brightness is nothing but a function of the accelerating voltage. So when you increase the voltage, you are going to have a high brightness electron beam. The next thing is going to the fine source size. This is nothing but the electron should be sourced from a smaller area so that you will have a focused electron beam on the exposed to the sample. Then you should have a good beam stability. This I'll be discussing when I talk about the electron guns. And it should have a small energy spread also. This also I'll come when I will talking about the different electron guns available. So the electron gun is supposed to carry out the role of generating electrons with the following characteristics. So before we go into understanding the electron gun, we should understand an important term called work function. So the work function is nothing but an amount of energy which is required to remove an electron from a metal base or a solid metal to an infinity. It means you are trying to eject an electron from the metal. So this is what is the work function is defined as. So this work function is generally defined in terms of 2 electron volts. And when coming to the electron guns, there are 2 types of electron guns has been put forth so far. First one is called the thermionic emission based electron guns. So the electron guns which works on thermionic emission is mainly based by heating. So the main contribution goes to Professor Owen Richardson. He got a Nobel Prize in Physics in 1928. So he was the one who suggested that when you are increasing the thermonic current in a sample by heating it, you are going to decrease the work function of the material. So by means, if you are this particular knowledge is provided here, and you can see this is a current density of J, and this is proportional directly to the temperature as well as the temperature. So which is going to be the heating of the coil or the filament. So when you are heating a filament, it is going to get a thermonic current, and by the way, we can reduce the work function and you can generate electrons. So coming to the thermionic based things, there are 2 different electron guns are conventionally used nowadays, and one is a tungsten electron gun. So this is how the tungsten electron gun looks like. You have a approximate 100 micron diameter tungsten is twisted like this, and this is what is magnified here, and this is how it looks like. And this is a directly heated cathode, meaning it will be heated by an electric. It will be heated by resistive heating, because since it is a metal, you will be applying a resistive electrical heating over this particular tip. And when it this is a work function basically for this tungsten. It is around 4.5 electrovolt. So when you are giving a sufficient amount of heating, you are going to cross this barrier. By the way, you are going to emit electrons from the surface of this tungsten thing. So another type of thermionic emission based thing is a lanthanum boride, lanthanum hexaboride based electron gun. The lanthanum hexaboride is a refractory ceramic single crystal material, this is an indirectly heated electrode. In the sense, it has a high electrical resistance. It cannot be heated like tungsten, what we discussed just now. So it is basically mounted on a graphite based carbon or a rhenium material, and this being an electrically conductive material, so you'll be heating this. That in turn heats the lanthanum hexaboride, and this is approximately 100 micron meter in cross section at the thing. And this electron gun can be of different shapes. Basically, you can have a tip like this, but you can have a flat thing like this, or you can have a sharp tip like this. So this is where it is positioned on this carbon or rhenium. So by heating this, you will be transferring the heat here, and because of that, the thermionic emission happens. So coming to the second part of this thing is a field emission electron gun, which is our main topic today. So as I was discussing about thermionic emission based things, where the heating is the main source for emission of electrons, whereas in case of field emission, this is going to be electric field will be the main cause for electron emission. So again, the same thing, you have a work function. So you will be applying a negative potential to the cathode tip. So that will generate, produce electrons. What happens basically is you will be having a very highly concentrated electric field at a very small area. So generally the field emission electron gun looks like a hairpin like this, where you get a sharp tip of a tungsten. It will be spot welded to a tungsten wire. This is a single crystal tungsten tip. This is actually made by electrolytic etching technique. So what is happening is when we are applying a negative potential to this cathode tip, you will be having since the area is very small near the tip, you'll be having a very highly concentrated electric field, so which is adequate enough to cross this potential barrier. As you can see, if you have a 3 to 5 kilowatt is given to this, you will create a field of close to 10 power 3 volt per micrometer area. So this is sufficient enough to cross this potential, so that you will start emitting electrons. And this particular technique, people call it as quantum tunneling. This is how the mechanism works in this field emission electron gun. And since there is no heating involved in this particular technique, we call it as a cold field emitter. Unlike the thermionic things where the emitting will be happening at higher temperatures. The second type of field emission electron gun is called as a Schottky field emitter. So here it is basically involves two things. Both the field as well as thermionic emission is happening in this case. So you will be having an electric field which will be reducing, will give a jump of some amount of work function is met by this electric field, where the remaining amount of energy has to be overcome by the heating. So why the name Schottky? Because we will be using a Schottky effect, wherein you will be applying an extraction voltage and heating simultaneously, which will be helping in emitting electrons. Similar to what we have seen in the cold Fe emitter, field emission emitter, you will having a tungsten wire spot welded to a tungsten pin again. So, but the additional thing what you have is you will be having a ZrO2 reservoir at the shank of the tungsten thing. So what happens is during heating, this ZR thermally diffuses to the cathode tip and it form a layer of ZrOx. So, and because of the heating, the electron starts coming. And you can see the tip radius is typically very less when compared to the gun what we have seen for the thermionic emitters. So this is a chart which is very important in terms of how each type of electron guns varies in different aspects. As we have been seeing, looking at the brightness, what we have discussed with the electron gun, and you can see the the field emission based things are going to give you the better brightness when compared to the tungsten or lab 6, where you can see the 2 order more thing is there. So another important aspect of the electron gun is, so the lifetime of the thermionic based electron guns are going to be very less. For example, in the case of tungsten, it's going to be only 40 to 100x, and whereas here it is maybe around 200 to 1000x. Whereas in the case of thermal field emission based, it is having a larger lifetime. In case, for example, the cold FEM can work for years, in fact. So now coming to the source size, as I was talking about the 4 important aspects, I was mentioning about the spot size. The spot size is determined by the source size. See, the source size of the thermionic based things are going to be higher. Say, for example, 55 to 100 micron. It means the electron is going to be, because we don't have a sharp tip in case of this thermionic emitted based electron guns when compared to here. So that's the reason why we are having a large spot size, and we'll be creating a large source size of electron. And if you look at the field emission based, and you can see there the spot size are very less, so we will have a focused electron coming from the field emission emitters. And now coming to the energy spread, which I was talking earlier also, the energy spread is nothing but, see, when you are accelerating at a particular voltage, say 20 keV, we are expecting to have all the electron from there to be at the same energy levels. However, in case of thermionic based emitters, the energy spread is going to be large, because you will have electrons with different energy levels, because that is going to cause a problem when we are focusing on some samples. I will comment on that later also. So now coming to the field emission things, as you can see, the cold FE has a very less, at least 1 order less, which was the energy spread is very less, which has that's the reason why it is having a better resolution possibilities are here in cold effect. So the current stability is one thing where I was talking about the stable beam. So in this case, you are this thermionic based electron guns have a better current stability when compared to the other things. Now, the another disadvantage of having a field emission is you require a very high vacuum levels in the electron column or the electron chamber to maintain it. Whereas this means the very high vacuum levels means you are going to have a very cost and the maintenance issues. Whereas in case of tungsten or lab 6, you will have the vacuum levels required are going to be very less. So coming to the temperatures which we are operating, so and as I was telling you, this is a heating method. So you have a 2500 degrees Celsius, whereas the lab 6 operates at 1600. The cold FEG operates as a room temperature, whereas the thermal FEG, which is having a field assisted heating, will operate at a 1500 degrees Celsius. So similarly, you can see there are a lot of advantages of both this as well as this. So coming to the next component is an electromagnetic lenses. So it is analogous, it is similar to the convex lens what we use in the optical microscopy. So the primary function of the electromagnetic lens is to focus the electron beam generated by the electron gun. The electron gun generated by the electron source is going to have a diameter of close to 50 micron. So what we require is we need to reduce the size of this electron gun, electron beam. Otherwise, we need to focus this electron beam on a particular surface of diameter close to 0.5 to 10 nanometer. So then only it is possible to scan over the area of interest and we can get the reliable information what we are looking at. So the role of electromagnetic lens is particularly to focus the electrons to get a beam size or a spot size of this particular size from here. So these electromagnetic lenses are made up of copper coils. They are enclosed in an iron casing with the cylindrical pole pieces. So this is how it looks like, and this is the pole pieces at a very magnified view. So what the electromagnetic lenses does? So we'll be applying an electromagnetic field over the electromagnetic lenses here, and it will in turn generate a force. So the electromagnetic field applied is going to have two components. One is basically perpendicular to the optic. This is optic axis. This is electron beam coming from an electron source, and this is the optic axis. So we have two components here. One is the field perpendicular to the optic axis. Another one is the field perpendicular parallel to the optic axis. We call it as a BR and BL. So the role of BR is, see, since you are, as we are talking about, you are having a 50 micron thing, so you have a lot of electrons coming in a very large wide range. So when it is coming close to this electromagnetic lens, because of this magnetic field, they are sort of deflected by this strong magnetic field, and they start taking a helical path, meaning it is getting focused. So this is the reason, this is the exact function what this electromagnetic lens is going to do here. It focuses the electron beam. So another thing is, since you are having a large magnetic field over here, it tends to deflect the electron whichever is coming here towards the center or the off axis or the near to the optic axis, which in turn actually focuses your electron to a fine beam. And then another thing, what is another interesting thing is, since we can apply different amount of current energy or field to the coils here, we can actually vary the focal length of the electron beam which is going down. So that is another important aspects. And this is the spot size. As you can see, the spot size what you can get from the electromagnetic lens is decided by this equation, which is a function of the accelerating voltage and inversely related to the electric field which is applied to the electromagnetic. So by varying the electric field and the accelerating voltage, it is possible to obtain the spot size what is required depending upon the sample requirements. So to start anything with, we are any microscopy method are going to have an aberrations. So I'll be discussing the very two important, or I can say the two important aberrations. So one is the spherical aberrations. As you can see, the spherical aberration is coming as just now we see the electromagnetic lens. The electromagnetic lens is going to place somewhere here. So it means that the magnetic field is going to be very high close to the region here when compared to the region here. So this is what the electromagnetic field is going to be stronger near the lens edge when compared to the optic axis. This is the central region. So because of this, what happens is the electrons very close to this lens are going to bend strongly by this strong magnetic field here. Because of this, the rays converge to form a disk rather than a point. So you'll have the different, you ideally want something like this which emerge here, whereas you have a strong magnetic field. Because of this, it is going to bend strongly and it is going to focus in somewhere here. So how you can prevent this we call it as a spherical aberration. So the prevention method is we put an aperture here just below the electromagnetic lens, so that these off-axis electrons are sort of filtered, and you will have only the electrons which are very close to the optic axis, and so that we can reduce the disk of least confusion, or you can say we can reduce this problem here. The second important thing is chromatic aberrations. See, the chromatic aberrations originate from the electron energy difference. Even though we are having a single accelerating voltage at this point, we are going to have electrons with different energy levels. So the different energy level electrons will tend to focus at different heights. Again, similar to there. So although the one energy level they may focus at here, so the another energy level may focus at here. So basically, this is a problem with this is mainly problem in thermionic emitters. This is what I have been talking about, the high energy spread. So in case of the thermionic emitters, you will be this delta E is going to be very higher. So which is going to have a this is going to have a problem when we are trying to focus the image. And apart from that, this is also the emission. This chromatic aberration is going to be much higher in the when you are having a higher lower acceleration energy accelerating voltage. If you can see, this is a typical example where we have 5 kV is given and the image looks like this. You can have the blur. Whereas if you are increasing the electron accelerating voltage to 20 kV, you are going to have a much clearer image. So before we look into the imaging part, I would like to give a glimpse about how the electron beam in fact interact with the specimen. Let us assume this is the specimen surface, and when the electron beam is focused on here, and it forms the electron beam interaction, we call it as electron beam interaction volume. And you can see there are different types of signals are going to come from this electron the interaction place. The first one is the Auger electrons. We have an Auger microscopy which will be giving some very fine details of the surface phenomena. And you can see this is these electrons are going to emanate from the very top surface of the sample surface. The next level we have a secondary electron. Again, this is going to come from a depth of 100 nanometer. Then we have a backscattered electron that is 1 micron level. It can the information is going to come from 1 micron depth. And next we have a characteristic X-rays which are going to come from a depth up to 5 micron. And this particular thing is going to be used for understanding the chemical analysis of the sample what we are examining. And there are also other things like Bemstrong extracts and X-ray fluorescence. And we also have some electron which is going to be transmitted and coming back directly down, and that is also used in some techniques. So this is a typical example of a simulated thing, how the effect of accelerating voltage on the beam specimen interaction volume. So we have an accelerating voltage of 5 kV here, and which is increased up to 30 kV on the same material, that is a gold, which is having an atomic number of 79. And you can see how the size looks when you have a very less accelerating voltage, and how you can increase the size of the interaction when you can increase the voltage. So what I'm trying to say here is, by doing this, we can, by increasing the accelerating voltage, we can actually increase the interaction volume. But depending upon the sample conditions, we need to work on the accelerating voltage. So during the electron beam scattering, and this is a typical diagram I would like to say, where we have an atom, we have a nucleus at the center, positive charge nucleus, and we'll be having multiple electron cells, K shell, L cell, M cell, and we'll be having electrons around here. So the electron beam interaction can be categorized in two types. One is elastic scattering and another is inelastic scattering. So coming to the elastic scattering, what happens is this is how it happens. So this is the instant electron coming from an electron beam source, and you have a strong positive nuclei here. So what is happening is, it is just deflected by this, because of this positive charge, this electron is going to getting deflected, and it is going to come down with the same energy. There is no transfer of energy happening here. So without losing any kinetic energy, whatever energy is in the instant electron, it will be almost here in the elastically scattered electron. So this is this particular elastic scattering will be higher when we have an atom with higher atomic number. That means our heavier atoms will have a higher angle when compared to the lower atomic number thing. And if you have a higher energy, then it will be overcoming the positive charge of the nuclei. Then the angle is going to decrease in case of elastic scattering. So coming to the inelastic scattering, this is another technique wherein you have an instant beam coming in, and what it does is it interacts with the electron shells around the atom, and it loses its energy during the interaction, and it comes back without it comes out or escapes out of the specimen surface. So during the process, what happens when it is interacting with the electron cells, it is like it will be knocking out some electrons out of this any of the shells, and that is going to give you the secondary electron imaging thing. So I'll discuss about it in the next slide. So there are two types of electrons I was talking about. One is the secondary electron, and another one is a backscattered electron, which are very useful for obtaining images during SEM. So the backscattered electrons, as we know, the beam electrons generally undergoes multiple elastic and inelastic scattering even within the specimen surface. So these elastically scattered electrons, which are having an angle is greater than 90 degree. So they comes out of the sample. They eventually find their way out of the sample, and like this, this will comes out of the sample, and it will be known as this phenomenon is called the backscattering. And this will be having the energy almost similar to the energy of the instant beam, and the technique which is used for capturing this backscattered electron is called a backscattered electron image. And as I was telling you earlier, this is going to be very with the this is very sensitive to the atomic number, so we can have a contrast imaging by using this backscattered electrons. So coming to the secondary electrons, these are nothing but the loosely bound outer shell electrons knocked off by the instant beam in an inelastic manner. So this is this outer shell electrons have information about the target or the specimen material. So this is again collected by a detector, specific detector, to get the secondary electron image. And since this secondary electron is coming very close from the surface, it is mainly used for obtaining the topographic contrast. And this particular graph gives an idea about this is the number of electrons which is being emitted, and this is the electron. This is the energy of the source, and you can see the BSE electrons are going to the very high energy because it is an elastic scattering. It doesn't lose an energy, whereas the secondary electron will have very less energy, within 10 electrovolt in fact. So and you can see the density of BSE electrons is going to be much higher when compared to the secondary electrons. So how this imaging is going to occur? So as you can see, the backscatter yield is approximately 10% for light elements. This is a plot. This eta is nothing but the which defines the backscatter yield, and this is nothing but the amount of backscattered electrons divided by the actual incident beam, the number of electrons from the incident beam. And you can see the backscatter yield is very less. This is the x-axis. We have atomic number of different elements, and this is the backscatter coefficient, that is eta. And you can see the low atomic elements are having yield less than around 10% or so, whereas the elements with very high atomic elements, they are having a much higher yield. So what it happens is the phase with high atomic number. For example, if you are getting an electron scattered from here, will appear relatively brighter. That indicates that you are getting a large amount of electrons scattered from this particular element or a material with the high atomic numbers. So a good example here is you can see if you are having an aluminum the atomic number of 13, and if you can gold as an atomic number of 79, and there is a contrast between this and this is around 69%. So when you have an aluminum somewhere here and copper, and again the contrast for 69, so we can clearly differentiate between the aluminum and Z based off the contrast imaging. Whereas in the case of the lower atomic number region, where in case of aluminum 13 and Z as 14, the contrast difference is only 6%. So what I mean to say is the Z contrast is stronger between two low Z phases when compared to the high atomic number phases. So the contrast needs to be at least greater than 10% if it wants to be identified in a SEM. So this is a typical image of an aluminum alloy, and this is a two-phase material, and you can see the aluminum with a low atomic number is seen as a dark or a gray, whereas you have a precipitate with a higher atomic number, which is seen as a very bright thing. So this is how the contrast microscopy was for the backscattered electron. So coming to the topographic contrast. So this is topographic contrast from this electron from the secondary electrons, and you can see they have a very low kinetic energy, and you can see, as I was telling you, it is coming from the surface of the sample. So if you increase when it goes to the depth is increased, or the depth of the electron, the secondary electrons coming from the higher depth have a very low energy, the intensity goes down very drastically. So it is only possible to capture the higher energy thing which is very close to the surface. And there are two types of secondary electron again. So one is SE1, we call it as SE2. This is, let us say, this is the sample surface, and the beam electron interacts here, and some secondary electrons come out immediately after the interaction with the sample, and we call it as a secondary electron. Whereas there is another case wherein you have this electron undergoing multiple elastic and inelastic scattering within the sample, and when it comes back to the surface, it again emits some secondary electrons by knocking out an outer shell, and this is Se2. So these two are very important in capturing the topographic contrast. Now, how the topographic contrast is mainly captured is, as you can see, this is a sample surface with some irregularities. There may be some groove, or there may be some topological difference. And you can see this is a primary electron beam, and you will see the electron gathered in this particular region is much higher. So the amount of electron gathered here is much higher, so that will give you the contrast between this region and this region, wherein you have only less electrons are being secondary electrons are captured by the detector. So these are some of the topography contrast images. This is some carbon with some holes, and this is a powder particle, and you can see how good you can capture the images. So looking at the applications, you have metallurgy and material science, as we all know, and there is a lot of application in electronic industries where the solder interconnect, the chips are also being done, and biology and biotechnology is another important field where the SEM application is tremendous. Even geologists and mineralogists use this SEM for understanding the rocks and salts, understanding, and of course the medical and pharmaceutical industries are another important stakeholder for this SEM. So to conclude with, this is an image of an ant taken at a very less magnification of close to 171,000 magnification, and you can see at a 15 kilovolt accelerating voltage, and you can see how beautiful it looks. Thank you all.
Thank you, sir. Thank you for your clear presentation. Right from image resolution, comparison with